Hey everybody, welcome to week 11 of PS 231. You don't realize it, but this is take 2 for me. I'm filming this on the Thursday before it's going to be sent out on Saturday, so let's see how this all turns out. So before we get started, I just want to say, so this is the beginning of the last third of the class, and if there's anything that you need or that can be done for you, please let me know. You've been working very hard, and I don't feel like I have no obligations to you. It isn't easy to stay in a hard class under any circumstances, much less under the circumstances that we find ourselves under. And although I have obviously very limited capacities, if there's any small thing that I can do to be of some help to you in these last 5 weeks of the class, please let me know. Even if I can't help you directly, which is a very safe bet, I may still be able to liaise in some useful way. One never knows. So far in the class, we've had sort of 2 major chunks, right? So chunk 1 of the class was the first 3 or 4 weeks, depending on how you want to look at it. And there we discussed the very rudimentary aspects of the things that we need for the rest of the class. We introduced what is a set, what is a function, how do we use logic to construct valid arguments. We talked about what preferences are, what a utility function is, and how it can help us to construct models. We talked about expected utility and how one can make choices under uncertain situations. And we discussed some basic rudimentary bargaining, Pareto optimality sort of notions. So that was chunk 1 of the class. And then chunk 2, the main part of the class, for I think 7 weeks we've discussed games of complete information. Games where everybody knows everything about the game. So we've discussed those with simultaneous moves. We just introduced the very basic concept of a simultaneous move game. And we discussed how one studies those through Nash equilibrium, both in pure and mixed strategies. After that, we talked about how to incorporate time into a fable of that type by talking about extensive form games. So we spent a whole week introducing extensive form games. We spent a week on subgame perfection and backward induction. And then most recently, we discussed how one analyzes the ultimatum game and other models that are more related to bargaining in a game theoretic sense. In what is a deviation from the syllabus, I will now be beginning the 3rd chunk of the class, the 3rd main module of the class, which is games of incomplete information. Games where I don't know everything about you maybe, or you don't know everything about me, or one of us knows more about the state of the world than the other one does. Something where not all players know everything / the same things about the game. This is a very exciting chunk of game theory. You know that something is exciting when somebody has to say to you, oh, this is very exciting. Prepare to be excited. This is very exciting. Can't you just tell how much excitement there's going to be moving forward? It's very exciting. But this is an exciting part of applied game theory, especially in political science, because so many of the interesting aspects of political processes, there's real wrinkles that emerge not just because of the strategic interdependence of the players in question, not just because of how their actions map together into utility functions, and not even just because of how time introduces a deep strategic interdependence in a dynamic sense. But there are other wrinkles that emerge because some players have the advantage of knowing more. Sometimes it's a disadvantage, although that's rare. Some players know more about the game than others. Some players know something about themselves that others don't. So if we're 2 countries thinking about fighting a war, and I know that I have nuclear weapons at my disposal and you don't, that seems like an interesting way to add a wrinkle to our interaction, doesn't it? You don't know how strong I am. You don't know that I have this terrible weapon at my disposal. And yet we might be bargaining. You're making really bad offers to me. You keep making bad offers not knowing how strong I am. This might be a cause of war in its own right? Similarly, two legislators engaged in legislative bargaining might not know each other's preferences perfectly. So if we're bargaining over how much to spend on a big stimulus bill, a relief package, and I have some ideal amount of money that I'd be willing to spend, and you have some ideal amount of money that you'd be willing to spend, we don't necessarily know that, and there are incentives at work that make us not want to tell one another truthfully. If I don't want to spend a lot on the package, I might come out with an offer even lower than what I'm willing to spend, not because that's what I hope to spend, but rather because I don't want to give you the impression that I'm willing to spend a lot. Well, that whole notion is ill-posed if we don't have a sense of incomplete information, private information, asymmetric information, information that one player has and another doesn't. Whenever you think about words like signal or communicate, it's an interesting idea. Let's suppose that I'm an autocrat and you are the citizens. And suppose that I want to signal to you that I am very strong. I'm willing to repress you if need be. I'm willing to be the rule of law all by myself if need be. Well, okay, but if there weren't multiple kinds of me, if there wasn't a strong me and a weak me, then the notion of my trying to signal something to you has precisely no bite. Right? If you knew everything about me, then I would have nothing to signal. There would be no way for me to signal because you already knew things about me. I'd be wasting oxygen. Right? If I tried to signal something to you that you already knew, or there wasn't even variety on that particular topic, then there wouldn't be anything interesting at work. So we need to extend our basic framework of introductory game theory to allow for incomplete information, to allow for the analysis of situations like that, where one player knows something and other players don't know quite how to react to that. In an introductory sense, this is the domain of so-called Bayesian games, Bayesian, Bayesian games. This is all sort of coming from the larger philosophical contributions of Thomas Bayes from a long ago, who contributed to statistics and to philosophy. We're going to be thinking a lot about how one learns, how one updates, how one assigns appropriate beliefs in situations like these where not everybody knows everything about the game. So much like with extensive form games and standard vanilla games, I just want to spend 1 week introducing the basic idea of a Bayesian game. My main hope is just that you can see that there's a lot of interesting and rich possibilities in viewing the world this way, and I don't think that it'll be very hard for you to open a newspaper and say, oh, well, I think there's some incomplete information dynamics at work between these two legislators, or these two countries, or these two Supreme Court justices. A lot of political processes have this flavor. It also isn't lost on me that you could probably use a breather after all these difficult problem sets that you've been doing, and so my sense is that just a straight-up introductory lecture where we just sort of think about the ideas a little bit will be of some use to you as well. So in the A block, I just want to extend our basic model of Bach or Stravinsky to allow for incomplete information. The idea here is that one of the players will be just a regular old Bach or Stravinsky player. That'll be me in this scenario. And that the other player, we don't quite know if they want to play Bach or Stravinsky as we've written it down up to this point, or if they actually want to avoid the obnoxious player 1 in this model. And this very simple, straightforward extension, it'll take a second, because you're gonna have to see things a little bit differently, the same but differently per usual. But my sense is that if we're just very slow and if we're very deliberate, just getting through that introductory example, a lot of this will be relatively straightforward after that. In the B block, I want to introduce an important class of models that are often modeled in a Bayesian way, the model of auctions. It might not occur to you, but auctions are a really important mechanism of transfer in political economy, and you might be thinking to yourself sort of what you see with antiques or something like that, some Banksy art show or something. But auctions are actually a much more general class of interactions than you might appreciate just at a prima facie level. So I just want to talk about what auctions are and what different kinds of auctions are. There's a million kinds of auctions, and it might be a nice opportunity to see some interesting institutional design questions. And at the same time, I'll be showing how incomplete information about how each competitor in the auction values the good introduces some really interesting wrinkles. And then in the C block, I want to introduce yet another interesting class of models that rely heavily on incomplete information. I want to talk about models of juries. So juries will be coming up a few times in the remainder of the class, and again, it's important just to get a good framework for how to think juries through. So I just want to introduce the basics of how one might write down a model of a jury, where the jurors are thinking about whether to acquit or convict a defendant in question. And we'll talk again about how incomplete information might introduce some important wrinkles that seem almost definitional to the problem of juries. So it should be sort of a smorgasbord sort of lecture today. Again, it's just more about introducing some fun ideas, some interesting institutions, some interesting mechanisms, some interesting modeling motifs that will be coming up for the remainder of the class. But still, I think that you'll find that you're better at learning in this buffet style than you had been up to this point, if only because you're getting a little bit faster, you're getting a little bit nimbler, you're getting more prepared for new wrinkles. That doesn't cause quite the face melting that it did before. So that makes it really fun for me, because now it's just a matter of showing you all the cool things that are happening, right? So I'm really looking forward to showing you some of this stuff. Let's get started. So I want to start off by just modifying our classic example of Bach or Stravinsky to allow for incomplete information. But in the name of completeness, let me just load up good old-fashioned Bach or Stravinsky as we've written it up to this point so that we remember just what that looks like. It's hard to believe that that was something that we were doing for a while there, right? So what's going on here in Bach or Stravinsky? Well, now I don't have to say the beginning of time anymore for a while. So once upon a time, and only that time, there were two people thinking about going to a musical concert together. And they wished, because they were musical companions, they wished that they could watch it together. So player one in this example, row player, can either go to Bach or go to Stravinsky. And similarly, column player can either go to Bach or go to Stravinsky. Nothing has changed. Precisely nothing has changed, okay? This is still just Bach or Stravinsky as you've seen it. And remember that our two players want to coordinate. So they hope to land at either Bach or Stravinsky. They don't want to get to Stravinsky Bach or Bach Stravinsky. Right? So we'll say that row player is the Bach lover this time. So maybe the payoffs for Bach are 2-1. The payoffs for Stravinsky are 1-2, and we've got zeros off the main diagonal. You'll remember that this game has 3 Nash equilibria, 2 of which are in pure strategies. The 2 pure strategy Nash equilibria are in fact Bach and Stravinsky. Those both represent mutual best responses. Those both are situations where no player would want to deviate. All of the same logic of Nash equilibrium will hold throughout the rest of the class. It's just a matter of extending our notion about what the source of uncertainty is to allow for more than just aleatory uncertainty, more than just strategic uncertainty through mixing, but indeed strategic uncertainty through not knowing other players' types. I won't get into all the nitty-gritty because I don't want to give you too many palpitations early in the lecture, but you'll remember also that this game has a 3rd Nash equilibrium. It's in mixed strategies, and the idea is that every player goes to their preferred show 2/3 of the time. So that's Bach or Stravinsky, regular old Bach or Stravinsky, vanilla, complete information, introductory Bach or Stravinsky. Now let me tell you a slightly different story. Suppose that I wanted to be your musical companion, same as before, and I wanted to go, and I could go to Bach or Stravinsky just like before. I make one and only one choice. I'm going to go to the Bach show or I'm going to go to the Stravinsky show. All right? But suppose that there was a new wrinkle. Suppose that I didn't know something about you. What's the thing that I don't know about you? Suppose that I didn't know if we were really friends. I didn't know if you were as dedicated to being musical companions as I was. Okay? So in particular, suppose that there's 2 types of you. There's a type of you that would like to meet me at the shows, right? That actually likes me. And there's a type of you that doesn't, that actually hopes to avoid me, that is happy when we are apart. So the version of you that wants to be friends, the version of you that wants to be musical companions, the type of you that wants to meet, is exactly as we've written the matrix up to this point, okay? So I'm just gonna make that's gonna be part of the model, but that's only gonna be part of the model now, okay? So I take the big game and I say, oh, it's actually part of a larger whole, all right? So this is the game where you want to meet me. This is Bach or Stravinsky as you've seen it before. This ain't your grandfather's Bach or Stravinsky though, because here's some more. So the idea is that there's going to be a second type of you, and we'll say that type of you is the avoider. We'll call this the meter and this the avoider, okay? So the idea here is that there's a second type of you that wants to avoid me, and it's just a whole nother game. It's just Bach or Stravinsky, same actions, same action profile, same Cartesian product, different preferences, okay? So the idea here is that the type of you that wants to avoid me is happiest at Stravinsky, but they're happiest actually at where I'm at Bach and you're at Stravinsky. So because we're talking about variation in you, the column player, actually you'll note that the row player is going to have all the same preferences as they did before. Their preferences in this version of the model don't depend on the type. I'm row player. I want to go. My very favorite is being at Bach with you. We're musical companions, and I love Baroque, right? My second favorite outcome is the one where we're both at Stravinsky. We're musical companions, and I'm okay with modernism. And my two least favorite outcomes are just the same, the ones where we're not together. All right? But the idea here is that the avoiding version of you is happiest when you're at Stravinsky and I'm at Bach. You're watching your favorite show all by yourself. You don't like hanging out with me. You don't want to be musical companions. Your second favorite outcome in this model, because you are the avoider now, is the one where I'm at Stravinsky and you're at Bach. Right? You're watching by yourself. It's not your favorite show, but at least you're by yourself. You're not listening to all my bloviation. And then if we're at the same show together, regardless, you get 0 happiness points. So the idea here is that you know which version of you are. You know which game we're playing, and I don't. I don't know which game we're playing. All that I know is half of the time you want to meet, and half of the time you want to avoid. I have only probabilistic expectations over which game we're playing. Suppose that I believe that you are the meet type with probability 1/2, and suppose that I believe that you are the avoid type with probability 1/2. So I don't know which game we're playing. I think I've got a 50-50 chance. I think there's a 50% chance that we're here and a 50% chance that we're here. And I have to make this one single best choice. Go to Bach or go to Stravinsky. It's the same choice that I had before, but now it is newly uncertain. Conversely, you know which game we're playing. You make two choices. And indeed, we're going to model you as if there were two versions of you, two copies. The meet copy of you is one player, and the avoid copy of you is another player. What do I mean by that? Well, I mean that you're going to be able to condition your choices over which type you are. Right? So I'm only going to say I go to Bach or I go to Stravinsky. You're going to be able to say I go to Bach if I'm a meter and I go to Stravinsky if I'm an avoider. You get to condition your choices on which type you are in ways that I don't get to. Similarly, we're going to have to think about whether each type of you wants to deviate from a given outcome. Right? So I'll be thinking through, is the meet type of you happy with the outcome that happened? Do they wish they could have made a different choice? And does the avoid type of you wish that they could have made a different choice? All right? That's the basic idea here, is that there's two yous, and I as an analyst have to handle them separately. Okay? So the way that I like to highlight who knows what is I will put, so you know which world we're in, so you get to know, I'll link these, I'll show that these are two separate information areas. So you can tell the difference between these two games, and I can't, right? So I've got this one big, there's only so much that I know about the interaction. You know specifically, you could tell one game from the other, and I couldn't. It's a lot like an information set. I can't detect differences between everything in the information set, whereas you can. So while we're here, I just want to talk about what a strategy is, maybe a little bit more precisely for each of us, okay? So because of the story I've been telling you up to this point, I make one and only one choice. I either go to Bach or I go to Stravinsky, all right? However, from my perspective, I'm watching you and I have to think about two independent choices on your part. You don't have to think about two independent choices because you know your type, right? I have to think about them both. The analyst and the other players have to think about them both. In other words, from row players' perspective, we can think about column players' strategy as a pair, as an ordered pair. What the meet type would do and what the avoid type would do. Okay? What would the meet type do and what would the avoid type do? So I can parenthetically, I can refer to your strategies as BB, Bach, Bach Stravinsky, where the meet type goes to Bach and the Stravinsky type, the avoid type goes to Stravinsky. I can do Stravinsky Bach, where the meet type goes to Stravinsky and the avoid type goes to Bach. or double Stravinsky. There's a band name, double Stravinsky. You heard it here first. Double Stravinsky. Called it. So that's what I'm right now. Let's think about this from role players' perspective. They're thinking, okay, conditional on these possible strategies by the column player, by you, I'm thinking through every possible pair of options that you might be doing. The Bach version of you, where both types of you go to Bach, the one where both types of you go to Stravinsky, and the one where the types of you differ in terms of which type goes where. And in fact, let's just think about this in terms of role players' payoffs. So role players' payoffs, we can put them into a 2-row, they go Bach, they go Stravinsky, 4-column, every possible strategy for you, where that's like which type of you does what. And let's just try to write down what role player thinks their payoffs are. Right? What is their expected payoff? Remember, they have to take an expected value here because they think that they're up against the meter half the time and the avoider half the time. So how do we think about those payoffs? Well, that means that every payoff for role player now is an expected utility, where the source of uncertainty is, I don't know which type of you are, right? With probability P, you're the meter, and with probability 1 minus P, you're the avoider, where here P is 1/2, right? So let's just try to fill in this 2x4 matrix. Let's try to think about what role players' expected utility is for playing Bach against each of these strategies where the expectation is about which type they're up against. Okay? This is easier than it sounds. So let's just zoom in on I'm playing Bach and you're playing Bach when you're a meter and Bach when you're a avoider. That's this top left cell. So we zoom in. Okay. Well, I'm playing Bach and I'm thinking to myself, well, if I go to Bach, half of the time you're the meter and you're playing Bach and I get 2 happiness points. And half of the time you're the avoider and you're playing Bach and I get 2 happiness points. So my expected utility for playing Bach, if I thought that you were playing Bach when a meter and Bach when an avoider, is 2. 1/2 times 2 is 1, plus 1/2 times 2 is 1, 1 plus 1 is 2. While we're here, let's just keep your strategy fixed and I'll think through if you were playing Bach both ways and I was playing Stravinsky, let's say I was playing Stravinsky, well, if I was playing Stravinsky against Bach, well, that means with probability 1/2, you're playing Bach, and I got Stravinsky Bach, and I get nothing. And with probability 1/2, you're the avoider who's playing Bach, and we're at Stravinsky Bach, and I get 0. So I get 0 happiness points in expectation for playing Stravinsky when you're playing Bach. We're gonna get some practice as we go here. We're gonna get some practice. What about Bach when the meter plays Bach and the avoider plays Stravinsky? This is when some real nuances happen. Okay. So what is the expected utility for role player playing Bach against Bach for the meter and Stravinsky for the avoider? Well, with probability 1/2, you are the meter is playing Bach, I'm at Bach with you, we're musical companions, I get 2 happiness points. So with probability 1/2, I've got 2 happiness points. And with probability 1/2, you're the avoider in this column is playing Stravinsky. Now I'm at Bach Stravinsky. I'm sad. We're not musical companions. I get 0 happiness points. So 2 times 1/2 plus 0 times 1/2 is just 1. So my expected utility for playing Bach when you're playing Bach when a meter and Stravinsky when an avoider is 1. Let's go down to me playing Stravinsky against you playing Bach when a meter and Stravinsky when an avoider. Okay, well, with probability 1/2, you're the meter and you're playing Bach, and I played Stravinsky. So with probability 1/2, we're at Bach Stravinsky. I get 0 happiness points because we're not musical companions. So that's 1/2 times 0. That's just 0. And with probability 1/2, you're the avoider. The avoider is playing Stravinsky in this column. And so I get a happiness point for being at Stravinsky with you. So that's 1/2. 1/2 times 1 is just 1/2. 1/2 is my expected utility here. Well, let's move over a column. How about when the meter is playing Stravinsky and the avoider is playing Bach? What's my expected utility for playing Bach in that situation? Well, with probability 1/2, you are the meter, and you are playing Stravinsky. I'm playing Bach, so I get 0 happiness points. With probability 1/2, you're the avoider who is playing Bach in this column. And so I'm at Bach with you. We're musical companions. I get 2 happiness points, and so my expected utility of playing Bach against Stravinsky if meter and Bach if avoider is 1. Is it starting to get monotonous yet? We're almost halfway through this matrix. I'm hoping it's starting to get a little monotonous, but not all the way just yet. There's a right amount of monotony for a class like this, right? And you're like, we're nowhere close. Well, let's go down to what if I played Stravinsky against you playing Stravinsky when a meter and Bach when an avoider? Well, with probability 1/2, you're the meter who's playing Stravinsky. We're together. With probability 1/2, that's great, right? So that's 1/2 times 1 for being in Stravinsky together. And with probability 1/2, you're the avoider. The avoider is playing Bach in this column, and so I get 0 happiness points for being at Stravinsky while you're at Bach. And so my expected utility of playing Stravinsky against Stravinsky Bach is 1/2. So far, you might be thinking, oh, we're 3/4 of the way to strict dominance, right? So 2 is strictly better than 1. 1 is strictly better than 1/2. 1 is strictly better than 1/2. Let's see what happens. The titillation is just driving me nuts. Finally, let's do this Stravinsky column. And let's think about my expected utility of playing Bach against that. Well, if I go to Bach, half of the time you're a meters at Stravinsky, I get 0. Half of the time you're an avoiders at Stravinsky, I get 0. 0 happiness points for playing Bach against Stravinsky. You may have expected that one. And in similarly not counterintuitive news, isn't it weird that not counterintuitive doesn't seem the same as intuitive? So here we are. So I'm playing Stravinsky and you're playing Stravinsky if a meter and Stravinsky if an avoider. Well, it's probably 1/2 where it's Stravinsky together, I get 1 happiness point. With probability 1/2 where it's Stravinsky together, I get 1 happiness point. That's 1. So the strict dominance thing fell apart. Thankfully, otherwise this would be pretty boring. So these are my expected utilities for playing Bach and Stravinsky against each of your respective options. Notice that I can just put in best responses. So if I think that you're playing Bach if meet and Bach if avoid, then my best response is Bach. If I think you're playing Bach if meet and Stravinsky if avoid, then my best response is Bach. If I think that you're playing Stravinsky if meet and Bach if avoid, then my best response is Bach. Finally, if I think you're playing Stravinsky if meet and Stravinsky if avoid, then and only then my best response is Stravinsky. So this is feeling kind of like where we were before, right? It was just a matter of using expected utility to sort of smush the two worlds together from player one's perspective. Player one doesn't have the luxury of seeing both worlds, so they have no recourse except to try to crunch the world into a single dimension using expected utility. Expected utility is a way to reduce the dimensionality of information. It's a way to take this giant world that we find ourselves in and smush it. So what should you do? Right? We can just go back to the two matrices because you're allowed to put in your best responses within each matrix. I didn't get to do that because I didn't know which matrix we were in. Right? I didn't know which matrix we were in. So suppose that the role player was playing Bach. What is each type's best response to that? So the meat type of you is thinking, well, I could go to Bach and get 1 happiness point for being musical companions with this person, or I can get 0 for going to Stravinsky. I'd rather meet the person, I'll take the 1. So against Bach, the meat type wants to play Bach. The meat type's best response to Stravinsky, similarly, is Stravinsky. Right? They get 2 full happiness points, so if they knew that the role player was going to play Stravinsky, then they would choose to play Stravinsky. What about the avoider? Well, the avoider is doing the exact opposite. The avoider is essentially trying to play matching pennies. So the avoider is saying, well, if I knew that role player was going to Bach, I would avoid them by going to Stravinsky. And if I knew that the role player was going to Stravinsky, I would avoid them by going to Bach. So we've got all those best responses pinned down. So consider the situation where the row player plays Bach, the meet type of the column player plays Bach, and the avoid type of the column player plays Stravinsky. Is that a Nash equilibrium? So this is B against BS. Well, we know that row player is best responding. We worked that out in their smoosh table, right? So row player's smoosh table said that against BS, that's that second column over, against Bach Stravinsky, they would rather play Bach, which gets them 1 happiness point in expectation, as opposed to Stravinsky, which gets them a half a happiness point, again, in expectation. Because the row player is playing Bach, the meet type's best response is Bach. That's what they're doing right now. And the avoid type of the column player is playing Stravinsky, which is their best response to Bach. So this is a Nash equilibrium, right? This is a Nash equilibrium of this strangely extended game where there's 2 types of you. Does that work every time? Well, let's think about if I'm playing Stravinsky and you're playing Stravinsky. So you play Stravinsky if you want to meet, and you play Stravinsky if you want to avoid. Well, we know that my playing Stravinsky is the best response to your Stravinsky. So if you're playing Stravinsky in both situations, then I, wanting to be your musical companion, have no choice but to go to Stravinsky. That was the best response in the rightmost column. And the meeting type of you is happy because if they deviated, if they switched columns within the meet matrix, then they'd just be doing worse. They'd go from 2 to 0. But the avoid type of you is not happy. The avoid type of you is stuck with me at the show. The avoid type wishes that they could deviate. The avoid type, if they could deviate, they would go to Bach and try to avoid me. So this is not an equilibrium. So it doesn't work that way every time. Bach against Bach Stravinsky is kind of special. For similar logic, Bach against Bach is not a best response. Is not a Nash equilibrium because the avoid type wishes that they could deviate to Stravinsky then. And Bach against Stravinsky Bach is not an equilibrium either because both types of you would wish that they could deviate. So in other words, this Bach against Bach Stravinsky is unique. Okay? But that's sort of the logic that we use. We'll talk more about equilibrium in the lectures to come. I just want to get you thinking about what analysis would look like in a model of this type. I won't get into the analysis, but there's nothing that stops us from having multiple, it can be more than 2 types of you. It might be 3 types. It might be 4 types. There might be many types of you. But more interestingly, maybe there's 2 types of you and 2 types of me. Maybe you don't know if I really want to meet or avoid either. So now I can use this information set sort of drawing to say, well, there's the world where we both want to meet. There's the world where I want to meet and you want to avoid. There's the world where you want to meet and I want to avoid. And there's the world where we both want to avoid. And I know which row we're in, and you know which column we're in. But where the entries are no longer cells, but rather are themselves games. I got meta in a hurry, didn't it? Think about all of the interesting, rich, strategic uncertainty there is about what kinds of players don't know what kinds of things about one another. We're allies. I don't know if we're really allies or not, and you don't know if we're really allies or not. I don't know if you really want to be committed to our alliance, and you don't know if I want to be really committed to our alliance. That could be two legislators talking across the aisle to one another. That could be 2 countries. That could be 2 faction groups trying to throw the sovereign out. There's all sorts of interesting things that we don't know about one another. And once, I don't know about you, but once you zoom out from one game to a game of games, did your mind just get blown? Mine just got blown again. My mind gets blown every time I think about a game of games. It's just so surreal, but you can also see that once you see it, it's immediately obvious that this is super useful for a wide variety of situations. Notice that this requires you to have beliefs about me as well, okay? So I just want to talk briefly about this notion about what beliefs there are, what probability a player assigns to the types that they don't know. In the previous example, I assigned probability 1/2 that you were a meter and 1/2 that you were an avoider, right? And maybe the same went for you in terms of once we got to the big game, or maybe you thought that there was a 90% chance I was a meter and a 10% chance that I was an avoider. Something like that. What are those beliefs? Well, those beliefs, they could be just straight up subjective beliefs. You're allowed to assign probabilities to things, right? People just randomly assign probabilities to things all the time. They have subjective beliefs about the appropriate probability that a given actor is of a given type. It could be that that's something empirically motivated, where you've done a lot of research on what professors are like when they choose a show to go to, and you estimated that 75% of professors are meters in such situations. Maybe you used the empirical record to inform your beliefs on that. So that's the basic framework of a Bayesian game. In lectures to come, I'll be a little bit more precise about what we mean exactly with that, but I just want to get this notion in your head first, that there's this zoom out game of games that happens where we don't all know everything about the game. I might only have probabilistic expectations about what type of player you are, and this then increases the dimensionality of my strategic problem in ways that force me to smoosh. I don't know why I said that with that particular accent, but let's just go with it. Smoosh the things together through an expected utility function. It's a really interesting framework. I hope that the next couple of blocks give you two cool examples of ways to think about incomplete information. And we're going to get started with one of the most important applications, auctions. So I'll see you over in the B block. So let's talk about auctions. I think auctions are an underappreciated part of political science. It might not be obvious. You're thinking about people at Sotheby's or whatever else places they do this sort of thing. And you're thinking, well, it's just a bunch of people with paddles. They're so important they don't say that they're bidding. They just kind of do this. You know, so suppose that my unenthused co-star was trying to bid. He's at the auction and he's like, oh, I really want that. I want that. You want a treat? I'll give you one after. He really wants that treat. And he's like, and then the auctioneer is like, oh, that's a wonderful bid. You bid at the auction, right? So you're bidding at the auction. And so Chewy really wants the treat. And so right now the treat, the bidding on the treat is $50. And he's like, oh, that's chump change to me. I'm Chewy. So he goes, and that means 55. And the auctioneer says 55. And then his competitor says, I bid 60. And then Chewy just goes, and that means he's up to 65. And then I said, I bid 70. You're not very enthused about this auction, little bear. So, and he goes, and that means that he's up to 70. And I'm like, I bid 75. And Chewy goes, and that's too much for my blood. I don't think that the treat is worth $80. So I'm done bidding. I'm done bidding. And Chewy is the winner of the auction. Yay! You want a treat?
Winner!
Right back. So the basic idea of an auction is that everybody goes into it. Chewy, me, Chancellor Jones, you, everybody. Everybody goes into the auction with some private valuation in their head. Right? They have a number in their head that they're willing to pay. If you're smart at auctions, first of all, don't go to an auction. If you don't know if you're smart at auctions or not, don't go. Because that means you're not. But if you're smart at auctions, you go in with a number in your head that you're willing to pay for any given good. Right? So I see just for the dumbest trinket that I could find in my office to motivate things. So let's say that this little sticker of Daniel Striped Tiger is what we're bidding on. Okay, so just think to yourself right now. Pause the video if you need to, although you don't have to think that hard. But how much is this worth to you? How much is this worth to you? I don't know, maybe $1 or something, right? So suppose that we all went into the auction, and let's say it wasn't private information yet. Let's just say that we all knew what everybody valued this at. You knew that you thought that this was worth $1, and you knew that you thought that Chancellor Jones thought that it was worth 50 cents. He's not a big Mr. Rogers fan. And you knew that I thought it was worth $50 because of what a big Mr. Rogers fan I am. And so we all knew each other's valuations. We all knew what we thought that the product that we were bidding on was worth. And what an auction is Just us continually bidding, ding, 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 ding. Or maybe we're just submitting an envelope. Maybe we just turn in an envelope that says we're willing to bid. There's lots of auctions of that style. And whoever is the highest bidder wins. And then they have to pay some amount. Usually, in your mind, it's the amount that they paid, that they bid. Oftentimes, however, in other kinds of auctions, what ends up happening is whoever wins is the person that bid the most, but they pay what the second highest bid was. That's called a second price auction. Auctions recently won a Nobel Prize in economics, or auctions didn't win the Nobel Prize. Two scholars who worked on auctions for a very long time in their careers and used it to learn how to properly distribute radio bandwidth or works of art or all sorts of other things. That's a very important process, and so auction theory is a very important area in social science theory. So if I'm trying to write down an auction game, what I do is I say I've got some set of bidders, 1 ... n. Auctions aren't very interesting if there's a low number of people. Usually you want to see a lot of people in the room, right? And suppose that it wasn't private information for now. Let's just keep going. And let's say that everybody had a publicly known valuation for the product. We'll call that V sub I. V sub I is how much everybody thinks the product is worth. The piece of art or the Daniel Striped Tiger sticker or whatever. Chewy's greenie. Don't worry, I gave him the greenie. Don't think that I just said the word treat around him that many times and didn't give him a greenie. Fear not. So everybody has a valuation of the good. That's just some number. It's some positive number. And in a simultaneous move auction, everybody just submits a bid. Everybody just chooses some bid. Call it B sub I. Some non-negative real number. Maybe you bid 0. Maybe you bid 0. That's fine. I've bid 0 at every auction I've ever been to. That statement is vacuously true. And also would be true. Unless they were auctioning off something really awesome. I don't think I would ever get involved with an auction. That sounds very terrifying. So a bid is just some B sub I. You choose some bid. And the interesting question is, does everybody just bid how much they value the product? Does everybody set their B sub I equal to V sub I? Does everybody truthfully reveal their preferences? Does everybody truthfully reveal how much they value the good through their bid? That's an interesting question. Why is that interesting? Well, suppose that you were the auction house and you actually wanted to learn what products were worth so that you knew how to appropriately evaluate other products. You wished you had data on how everybody valued this product. Well, if everybody's lying, then that data is not very much use to you, right? You want truthful revelation. You want everybody to bid in a way that reveals. In this case, there's nothing to reveal so far because there's public, it's all known how much we all value the good. So we have a bunch of players, we have a bunch of bidders, and they all have a valuation, and they all make a bid. Okay, so these are the beginning rudiments of an auction. And then last comes the expected payoffs, which are a function of what kind of auction we're having. So for example, if we were running just a standard simultaneous move first price auction, sealed bid, first price, then we all submit our bids, B sub I. Whichever is highest is the winner, and they get to pay, and they get to enjoy the good, but they have to pay the cost. So maybe their utility for that is V sub I minus B sub I. How much they like it minus how much they paid. Simple. And everybody else gets 0. So here, the losers don't have to pay. There's no rule that says that. Maybe instead, maybe it's an all-pay auction. In an all-pay auction, you could take the same exact profile of valuations, the same exact profile of bids, and turn it into a different set of utilities, because then the winner would get to enjoy the product. They would get V sub I happiness points for having the product, but they'd have to pay their bid minus BI. But everybody else would have to pay their bids too. Suddenly everybody would bid 0, right? You wouldn't get truth or revelation because they would actually have to pay. A very common auction that's of theoretical relevance is a second price auction, sealed bid, second price, winner pay auction, where the winner gets the good. They get VI happiness points for having won the good. And they don't pay BI, they don't pay their own bid, which is the highest bid that was made, otherwise they wouldn't have won. Instead, they get to pay the second highest bid. They get to pay the maximum among all bids that aren't them. That's just another kind of auction. And if it's winner pay, then everybody else gets zero. Nobody else has to pay. So in other words, an auction is a bunch of bidders, a bunch of valuations, a bunch of bids, and then some mechanism, some institution that determines how to send bids and valuations into utilities. Different institutional structures, different kinds of auctions generate different utilities and therefore will incentivize different kinds of equilibrium play. So that if you were an auction house and you're deciding how you're going to run your auctions, your goal might be to maximize revenues or to maximize truthiness of the bids or whatever. You have to choose among all these different institutional options. You have to choose a kind of auction to run at your auction house. And that will have massive differences in terms of what happens. Now, you might be thinking, oh, what does auctions have to do with politics? So just think about lobbying real fast. Just think about lobbying. Two bidders from two different political action committees are trying to win the vote of one of the representatives in Congress. Okay? And they bid, and they bid, and they bid. They make contributions. They take them out to dinner. They provide information and literature. Maybe they're part of an amicus brief somewhere. So they invest time, resources, money into trying to win the vote of this person. And then the representative declares a winner. They turn bids into victory. Okay? Notice that all pay auctions are the norm in lobbying, though. The legislator doesn't say, and here's a refund. Here's a refund. Here's all the money. I'm sorry I didn't vote your way. Here's all of your investment back. They don't do that. So that's an all-pay auction. Okay? And it's sealed bid in a sense because, I don't know if you know this, but rival political action committees don't typically tell one another what they're doing. I mean, they have a sense because of strategy, but they aren't open. It's not observable moves in the sense of a finger game, right? So lobbying is just an auction with a particular kind of cost structure. War is just an auction with a particular kind of cost structure. Auctions are everywhere, not just for art. And you may be thinking to yourself, well, what's this have to do with private information? Well, do people at auctions go around saying how much they value something at? I've never been to an auction. It's like a dinner party for me. But I suspect, from what I've seen on Antiques Roadshow or whatever, that people don't just walk around saying, well, I intend to bid $10 on that item. You can know that. That's worth $10 to me. Nobody says that. Nobody says that. Nobody in an auction walks around saying, oh, that looks pretty great to me. If anything, they go around looking unimpressed so that people think that there are low valuations. They don't want people to think that they love this because then there'll just be more bidding. They'll have to pay more. That's stupid. Don't do that. Right? And then there's always the people on the cell phone. There's always the cell phone bidder guy. So in other words, in auctions, more often than not, those valuations are not publicly known. I know how much I value the good. I know my own VI, but I don't know your VI. Now, I might have a sense, right? If it's a giant mansion, I don't think that your VI for a giant mansion is $0, right? You would like to live in a giant mansion. I would like to live in a giant mansion. Chewy, less so. He really likes to snuggle. I have a guess. I have a range of possibilities of what I think you might value something at, but I don't know for sure. I don't know your valuation for sure the same way that you do. You have private information about how much you value the product. Don't you think that's going to influence how I bid? If I thought that you loved the product and I had to submit one and only one bid, I got to think to myself, do I want to beat you or not? Because if I beat you and it's a first price auction, so I have to pay the whole bid, absolutely not. I'm not going to do that. So in other words, my resource investment depends not just on how much I value the product, but also on how much I suspect that you value the product, and in particular, how that interfaces with the institutional design of the auction in question. If I have to pay the whole bid, I don't want to get involved with that sort of thing. So what I'm trying to instill here is a two-step process. One, many important competitively strategic aspects of politics can be modeled as if they're auctions. Lobbying and war especially come to mind. Right? Special interest politics in general is very much the world of lobbying and contests. Okay? War, you're investing resources in something that you don't know if you're going to win, and you're going to have to pay no matter what. Those lives don't come back. Those salted fields don't come back. Those destroyed factories don't come back. You have to pay the costs of your bid, where your bid is fighting, where your bid is lobbying. So that's step one. Many important competitive aspects of politics are like auctions. 2, auctions are obviously the domain of private information. Clearly, both how auctions transpire and what sort of choices we want to make about what kind of auction institutions to set up depend very strongly on what the informational environment is. So if you can see the world as if it's an auction, then you have a very good avenue for thinking about the importance of information and institutions simultaneously. Auctions are gold. Auctions are beautiful. And this is a subjective thing. I mean, a lot of this class is subjective. Subjective in the sense that it reflects my own taste and preferences as somebody that knows a little bit of game theory, as an instructor, as a scholar, as a movie maker, right? And so I'd like to talk about auctions a little bit more maybe than average, but I also just think it's a great way to see this. And I hope that you agree, and if not, there'll be other examples. But auctions, it's a liberating feeling. The first time, it's just another avenue for creativity. It's a way to think about different processes that we care about. You can think about elections as auctions, right? Where we're thinking about, if we're two parties, we're thinking about how much to invest in a given district. Is it a very competitive district? Is it a very non-competitive district? How do we choose how many resources to put into 435 separate auctions? 435 related but separate auctions for the House of Representatives every 2 years. The parties have to decide, not just the candidates. The parties have to decide where to send their resources about where to have competitive candidates, where we're going to have a lot of TV ads, etc., etc. That's just a bunch of auctions being held. You don't get a refund if you lose. So that's auctions. It's a very interesting class of interactions, and it's a very interesting class of game theoretic models that pin down those interactions. I want to conclude with one more of those by talking about juries over in the C block. So suppose that we were on a jury together. Whoa. I got heavy in a hurry. And we're deciding whether or not to acquit or convict the defendant at the trial. Now, we go into the trial with maybe we have the same basic idea, maybe the same prior belief about whether or not the defendant is guilty or innocent. So we go in knowing that there are two possible states of the world. There's the state of the world where the defendant is guilty, and the state of the world where the defendant is innocent. And we'll just call those G and I. Those will be just two separate worlds, the same that we've been interpreting up to this point. And we'll suppose, just for an animating example, that we suppose that the person is guilty, that we think the defendant is guilty 1/3 of the time, and thus is innocent 2/3 of the time. We could choose different probabilities, it's no big deal. So we go into the world thinking that. So I've never been on a jury before, and I don't know if you have or not, but I suspect that more often than not, there is not immediate consensus, right? So different jurors have different beliefs about the guilt or innocence of the defendant that they may have obtained from the trial. So even if we came into the trial with the same beliefs, the same sort of rough first guess about the guilt or innocence of a given defendant, the trial happens, and then we derive our own judgments about what happened there. That might sound like an incredibly not rational sort of thing, but actually it's modelable in a very straightforward way. In broad brushstrokes, our goal as a jury is going to be to try to convict guilty defendants and acquit innocent defendants. And the idea here is that we will be punished if we convict a defendant that is innocent, and we will also be punished if we acquit a defendant that is guilty. So suppose that you and I were playing a game of two angry people. So the idea goes like this. We're going to be a jury of two people. This is me playing on 12 Angry Men. If you haven't seen the movie, the old version of 12 Angry Men, it's a really great movie. It's about a jury and what happens during their deliberations. It got remade in the 90s. The remake isn't terrible, but it's not as good as the old one. I hope that they remake one now where it's like, well, there's 12 angry people. And I mean, there's a lot of interesting dynamics at work. It's based on a teleplay. And so it's a little bit literary. There's a lot of interesting character level dynamics among the 12 jurors. And it'd be great if they redid it. But the old one, Henry Fonda, really amazing. Highly recommended. So suppose instead of 12 jurors, you and I are on a jury together. All right? We're the only two. And there's a defendant, there's a trial, there's a defendant. And the defendant, we don't know. We don't get to know. It turns out that jurors don't get to know. So we don't know if the defendant is really guilty or really innocent. Where that's just a philosophical can of worms I don't want to get involved with, but let's just say in a statutory sense. So we don't know the true state of the world. The true state of the world is either that the defendant is innocent or that they are guilty. And I'll call those, I'm going to use these little omegas to be the state of the world. Omega equals innocent, omega equals guilty. And you're like, I thought we were done with Greek letters. No, I'm afraid not. So we don't know the true state of the world. Now, that's a bummer because the true state of the world is going to determine what our payoffs are for conviction or acquittal of the defendant. In particular, we want to convict guilty. If the state of the world is guilty, we would like to both vote to convict, unanimously convict. And if the state of the world is innocent, then we would like to not convict, which means that at least one of us voted to acquit. So typically in juries, in criminal proceedings, it takes unanimity of the voters to convict. And if there's a single person that says no, we should acquit, then it's an acquittal or a hung jury. So in other words, in one state of the world, we would like to coordinate on voting to convict, and on the other, we would like to not do that. Okay? And we don't know the real state of the world. We don't know if we're in this world or in this world. We don't know that. We don't get to know that. We go in with maybe we have a common probability. We go in just based on the real world that we've experienced. We think that there's some plausible probability that the person is guilty. So suppose that we think that the defendant is innocent with probability 2/3 and guilty with probability 1/3. That's just to animate things. So we go in and there's this common probability. And we could put in payoffs. So let's say that we were thinking about our convict-acquit decisions. So in the world where the defendant is innocent, which we don't get to know, but if that were so, then if we both vote to convict, they will be convicted because we have unanimously convicted them, and we will be punished. The idea is that we get punished for making the wrong choice here. We've made an error. We took an innocent person and we sent them to jail. That's awful. So to encode that, let's call that minus Z for both of us. So minus Z is the punishment for wrongly convicting an innocent person. Z is going to be some number that lives between 0 and 1. Okay, so the idea here is that if Z is very high, then we value not convicting innocent people quite a bit. Okay, so Z is just some number that lives between 0 and 1, so that punishment could be like minus something really close to 0, minus something really close to 1. And we get 0 otherwise. So if one of us votes to acquit, then it's 0. And if both of us vote to acquit, it's not like you get a bonus for it being unanimous. So that's 0-0. So the idea here is we want to avoid punishment. We want to avoid wrongfully convicting an innocent person. Same sort of idea is going to go over here in the world where the defendant is actually guilty. So if that's the case, then if we both vote to convict, we get 0-0. So that's the cell where we get 0-0. We did the right thing. And everywhere else, if we fail to convict a guilty defendant, then we get -1 minus Z. So Z tells you how much we relatively care about convicting innocent people versus acquitting guilty people. Okay. So the idea here is that if Z is very high, if Z is very close to 1, then we really, really, really don't like convicting innocent people relative to acquitting guilty people. And if Z is very low, then it's the same in reverse. So we go into the trial. We have a common prior probability. We both think that there's a 1/3 chance that they're guilty and a 2/3 chance that they're innocent. We go into the trial, we have a sense of the structure of the game. This all seems very straightforward, okay? We know what voting looks like. There doesn't seem to be any confusion, okay? There also doesn't seem to be any avenue for asymmetric information. Now, we both have uncertainty because we don't know for sure whether or not the defendant is guilty or innocent. But we know each other's beliefs right now. We know everything about each other's judgments. The only thing that we don't know is the true state of the world. Well, there's a way that we could modify that. You know, it might not sound very rationalist to start, but many jurors go into experience trials differently, right? So jurors can receive different cues. They might interpret evidence in different ways. They might have genuinely different readings about what happened at the trial. They might like the prosecutor at different degrees. They might like the defense attorney at different degrees. They might really think that physical evidence is important. They might really value witnesses differently. You know, all sorts of differences emerge. And it's like, well, do I have to think about all that? No, we're going to use information. We're going to use private information as our way of amalgamating all of the different ways that jurors experience trials differently. We're going to say, you know, there's all sorts of different ways for that to be the case, but the thing that really matters is the effect that has on the belief that the defendant is guilty or innocent. That's the thing that really matters here. The thing that really matters isn't if you really care about physical evidence or if you really care about witnesses. The bottom line is how much does that influence your probability of thinking that the person is innocent or guilty? That's the bottom line. The bottom line is the informational effect that your subtle differences in how you weigh evidence has. Otherwise, we're going to be stuck here forever because none of us is a criminologist. Maybe some of you are criminal justice majors. It's an interesting thing to think about, right? Oh, you've been waiting for my validation, I know. This is not something that I can credibly claim to be an expert in. However, we can think about it in this reduced form bottom line version where the thing that really matters is how these differences have informational consequences. So suppose that we each received a signal. Suppose that we each received a signal during the trial. We each got a signal. Okay, S sub I. And S sub I is either we got a signal that the defendant is guilty or we got a signal that the defendant is innocent. We got some signal. Okay? We each noticed a different thing from the trial. We each locked in on a different piece of evidence. Something like that. And the idea is that we receive signals differently depending on the state of the world. So I'm going to say P is the probability that each juror gets the signal of guilt conditional on the state of the world actually being guilty. Which is to say, P is the probability that the juror receives the correct signal of guilty. So if the state of the world is G, what is the probability that my own signal SI equals G is P, where that's greater than 1/2. We're gonna think that these people are relatively smart, so they're likely to get the right signal, but not perfectly likely. And that's going to reflect those subtle subjective differences in how we weigh evidence. Similarly, we're going to say that Q is the probability of correctly receiving a signal of innocence. So with probability Q, if the state of the world is Q, then the probability that you receive the signal innocent is Q. So we'll say that P is strictly greater than 1/2. The probability of correctly getting the guilt signal is greater than 1/2. And we're going to say the Q is greater than 1/2, which means that they receive the correct innocent signal more than half the time. So this is all relatively optimistic. So then we use the signal to update our beliefs. We get the signal and we use it to update our beliefs about the guilt or innocence of the defendant. So after we receive the signal, our probability of guilt is no longer necessarily 1/3. It might be that we change our beliefs in really interesting ways. So in order for me to talk about that updating process, we need to talk about Bayes' rule, which is why we call this Bayesian games in the first place. So Bayes' rule is just a way to update your probabilistic beliefs about something after receiving a signal or some other piece of data. So you go into the world with some prior set of beliefs. So maybe you enrolled in this class with a prior set of beliefs that it would be easy or hard. And then you took one class. You sat in for a lecture, you did one problem set. That sent you a signal, and you updated your beliefs. Maybe you thought it was a 50% chance that this was a hard class. You go to one lecture, you receive a signal that this is in fact a hard class. You do a problem set, you receive a signal that this is in fact a hard class. You update your beliefs. You have a new probabilistic expectation that this class is hard. You don't immediately infer for sure that all 14 weeks that are left of the class are going to be hard. But you do update your beliefs, and you probably have a higher belief that this is a difficult class. Similarly, if we went into a jury trial and you had a belief in your mind that maybe there was a 1/3 chance that the defendant was guilty to begin, that was your initial prior belief. And then you received the signal that the defendant was guilty. You interpreted the evidence in that way. Well, if that's the case, then your belief is no longer going to be 1/3. You won't think that it wouldn't be reasonable for you to think that they're innocent for sure, because you know that you only get the correct guilty signal probabilistically with probability P. So you don't know for sure that the information you got is right, but you have to go on it. You need a principled way to turn new information into new beliefs. You come in with an old belief, you get some new information, you need a new belief. That's Bayes' rule is the tool that we use for that. And the basic idea of Bayes' rule is the following. You need to think through, if you want to come up with the correct new probability that you think that the defendant is guilty, conditional on receiving a signal. Let's say conditional on receiving the signal that they actually are guilty. So you want to know, what's my updated belief that the defendant is guilty, conditional on the fact that I just received a signal that they're guilty. I interpreted the evidence from the trial that they're guilty. What's the appropriate mechanism to do that? Now, this isn't a probability class, so I'm just going to very quickly tell you how it works in this particular example. If you want to know more about Bayes' rule and where it comes from, ask me sometime. We can derive it ourselves if you'd like. It's not very hard to do. So it turns out that the probability that the defendant is guilty, conditional on having received the signal of guilt, works out like this. In the numerator, it's going to be a numerator-denominator thing. In the numerator, it begins from your prior belief that the defendant is guilty. That was 1/3 in this example. And you multiply that by the probability of receiving the guilty signal conditional on them being guilty. Well, we introduced that. That's P. That's the probability of receiving the correct signal of guilt. So what is the probability of receiving the guilty signal conditional on it being a guilty defendant? So that's our numerator. Sometimes you see that the prior times the likelihood. Those are just terms that come up sometimes. And we need to divide that by something. Well, we divide it by that same thing that we just came up with, the probability that they're actually truly guilty, my prior belief of actual guilt, times the probability of receiving the guilty signal conditional on guilt, times the probability that they're innocent, 2/3 in this case, my prior belief that they're innocent, times the probability of getting this guilty signal conditional on them actually being innocent. The probability of getting a guilt signal when you wish that you had gotten an innocent signal, that is 1 minus Q. Q was the probability of getting the correct innocent signal. That means that 1 minus Q percent of the time, when they're innocent, you get this guilty signal. 1 minus Q percent of the time, which is less than half the time. You think that you're like, oh, the signal that I got from this trial was that they're actually guilty. So we receive our signals and we update our views about the guilt or innocence of the defendant. Now, if we got the same signal, then we update our views in the same exact way. We would end up with the same new beliefs. We would end up with the same new updated beliefs of guilt or innocence. But if we receive different signals, if we got mixed signals from the trial, then our updated beliefs will diverge. If I got the guilty signal and you got the innocent signal, then my beliefs will go up from 1/3 and your beliefs will go down from 1/3. Okay? Appropriate jury voting then in this example, in this version of the model, is about weighing the relative demerits of convicting innocent people and acquitting guilty people, your prior beliefs of guilt or innocence, and the signals that you receive at the trial. So this introductory theory of juries, now I know what signal I got, and you know what signal you got, but we don't know what signal the other got. So it'll get very overwhelming here very quickly if I try to do too much more. We're very long into the video. And so I just want to stop there because I want to introduce this logic of juries. I just want to get you thinking about how jurors would evaluate evidence based on the private signals that they receive during trials, their own private evaluations of things. Everybody saw the same trial, but that doesn't mean we all evaluate it the same way. That doesn't mean we all get the same signal out of it, right? Two people can go to the same movie and get very different views on what the movie was about, much less whether or not it was any good. The same goes for trials. I'm not saying that with any value judgment. That's just descriptive. I'm not sure if you noticed, but two people can watch the same trial and come out with very different views, even if they entered with the same prior belief about the guilt or innocence. Right? So for all you pre-laws there, this is the beginning of how to think through the process, the very human process of accumulating evidence in a principled way, and doing so with the strategic interdependence where you don't know if everybody saw the trial the same way that you did. So what do we talk about today? It's a good question. We were a little bit all over the map, but we introduced the basic idea of not knowing. So the players in our games, other than lottery tickets, have known an awful lot. The only time that they haven't known what's going on in a strategic sense is when at least one of the players is mixing. Sometimes they throw a fastball, sometimes they throw a curveball. We saw that mixed strategy Nash equilibrium had a lot more nuances than pure strategy Nash equilibrium. And an analogy can be drawn between incomplete information game theory and complete information game theory, where there's just a new dimension of uncertainty brought into it. And the associated strategic interdependence where I know my own signals and you know your own signals, but we don't know what signals the other received. Whether it's an auction or a jury or figuring out what kind of concert to go to or how hard to fight in a war or whether you should fight in the war at all, who you should vote for or where you should campaign. All of these strategically competitive situations where you don't quite know how hard the other person would fight if it got down to it. That's a really interesting class of interactions, and we need to work through some of these nuances to be able to think about it in a principled way. Now, it's going to be difficult. It's going to be hard. These videos, my sense is it got a little bit easier when we got to the finger games, and I was able just to zoom all over the screen. You don't have to listen to me as much, which I'm sure you were happy about. But now we're going to have to stop and think quite a bit. Over the next 5 weeks, there's going to be a lot of stop and think moments. I might have to tell you to take your pencil out of your hand. And I don't mean anything by that. This has happened a few times, and I'm really sorry if I tell you to put your pencil down. It's just because you're not ready to write yet. Sometimes you need to stop and think. And this incomplete information game theory stuff, there's a lot of stop and think moments. And I'm looking forward to going through that with you because I think it's an important skill to learn how to stop and think and not get too angry about it, because you're going to have to do that moving forward for the rest of your life. One interesting thing about the way that we went through today was we started off with, there are types of players. I don't know if you are a meter or an avoider. I don't know which type of player you are. I don't know what your preferences are. And by the end, we saw that it wasn't so objective as what type of player you are, and it kind of turned into how did you subjectively evaluate the evidence at this trial, and what potential ramifications might that have on your decision about whether to acquit or convict. That's an interesting subjective human wrinkle in an otherwise robotic class, and it's with that in mind that I'd like to conclude with a provocative thought. There's an influential and true idea that rational players, rational actors, the robots that we've been modeling up to this point in the class, are not capable of agreeing to disagree. If they're faced with incomplete information situations, worlds where there's uncertainty, then the same players, equipped with the same data, the same prior beliefs, that receive the same signal. So if we're two rational players, we had the same prior belief and we got the same signal. We're two jurors, we had the same priors about guilt or innocence, and we got the same signal at the trial. We used the same Bayes rule machine and we came up with the same updated beliefs. Rational actors can't agree to disagree. This is an important truism in subjective probability theory, which, you're probably not going to take a deep subjective probability theory class, but it's an interesting thing to think about how people come to evaluate probabilistically the relative likelihoods of a bunch of different outcomes that they don't quite know for sure what's going on. They don't know the true state of the world. They don't know whether it's going to rain tomorrow, but they watch the same news report and they have the same knee pain or whatever old people get when the humidity is coming. And so they came to the same probabilistic evaluation both prior to getting data and post. And rational actors can't agree to disagree. They must come to the same decision every time. But we just saw in the C block that there's a lot more to it than that. There's no rule that says that two rational actors, no matter how similar they may be in terms of their strategic DNA, there's no law that says that they have to get the same signal. Right? They might come to their own subjective and divergent probabilistic beliefs about the guilt or innocence of a defendant, or the strength or weakness of a military opponent. They can come to different evaluations of that. We just have to be smart. We have to say, well, the Bayes rule machine is really strong, but it turns out that two otherwise identical actors can get different signals, and that's our way of modeling otherwise identical actors that weigh evidence differently. Weigh data differently. We don't care about the differences in those processes. That's a psychological thing, that's a sociological thing, that's a political thing, but it is outside of the domain of rational choice theory in the standard treatments. And so the question I want to put to you is that sufficient? Is that little modeling trick of saying two otherwise identical and rational actors who would be forced to agree can be allowed to disagree just by giving them different signals? Or do you actually think that two intelligent, contemplative, I'm not going to say rational, do you believe, and I don't know the answer to this, two intelligent, contemplative people can see the same thing, have the same experiences, have the same data, and come to divergent views on something? Is it true that two people who are otherwise identical have had the same experiences? Could they evaluate evidence differently at a trial? Could they get different signals from the same trial? Because that's the workaround that we used. We said, well, agreeing to disagree doesn't sound good, and Bayes' rule is very strong, and so our little workaround here is going to be to say that these agents with the same data, the same experience, the same exact prior belief, we went in thinking it was 1/3 guilty. We had everything the same, so we must have been identical. We had everything the same, so we must have been identical. Could it be that two actors that are identical enough to have the same prior belief of guilt or innocence before day one of the trial, could they get different signals from the same trial? Because that's our way of saying that rational actors, they can't agree to disagree, but they can see the same thing two different ways. Now, this is just one of those provocative questions that you should hear in college. Can two otherwise identical people see the same thing two different ways? That's a really nuanced and difficult philosophical problem, okay? You're not going to have a firm answer to it immediately. It's a great thing for dinner parties, I'm hypothesizing. But your answer to that is, again, very telling and very interesting, because that's going to have an influence on how you navigate information and strategy moving forward. Some of you are going to become lawyers. Some of you might become defense attorneys or prosecutors. You might become trial lawyers, okay? You're going to have to think that through. You're going to have to think about whether or not you want a homogeneous set of jurors that you think you can send the same signal to them all, maybe, or maybe even though they're identical, maybe they'll all get different signals. Or do you want a heterogeneous set of jurors where you don't quite know what their prior beliefs were, but you might be you might be better able to make sure that they all get the same signal? Whether or not you think that you want a homogeneous or a heterogeneous jury depends very strongly on whether or not you think that two identical actors can get different signals from the same trial. Whether or not you think that in a weak sense they can agree to disagree, because they surely can't agree to disagree in the strong sense that two otherwise identical actors just came to a different belief. They use I used Bayes' rule and you use something else. That's not allowed in our models. The perhaps more provocative follow-up is, why did you answer the way that you did? I can think of two classes of answers. One is that you thought about the outcomes that would arise. You were a consequentialist, and you thought about the outcomes that might arise from one view of the situation and another view of the situation. You didn't have a strong belief going in about whether or not two identical jurors could come to a different view from the same trial. But you thought about, well, if they didn't agree with one another, then that would be good because that would mean fewer convictions because they need unanimity. And therefore, because I don't like convictions very much, or my personal Z is very high, I really don't want to convict innocent people. Therefore, my view on the subject is that two people can agree to disagree. That's a plausible answer. The other plausible answer is that maybe you're a psychology minor and you've thought through different cognitive processes and there's sensory limitations. There's all sorts of differences in the people, right? We see things differently. We hear things differently. We what's the verb for cognition? We cognate our way through things differently. We're just different, and our processes are 100% different. And therefore, it was folly to ever think that we could expect to see unanimous views on these things, because people's, even if they're identical, their processes might differ very much. So in other words, the follow-up question to why you feel the way that you do is itself also telling about whether or not you're sort of a proceduralist or a consequentialist in a weak sense. I'm asking you these two questions because a lot of what's to follow in incomplete information game theory is about making a bet. When I didn't know if you wanted to meet or avoid me going to Bach or Stravinsky, I had to make a bet, and I bet on Bach. Okay? Because I thought there was a 50-50 chance, and I want to go to Bach. I like Bach more. It's my best response most of the time. I bet on Bach. You didn't have to bet on anything. You knew which type you were. You didn't have to make any bets. And I think that that's an analogy for how you feel about agreeing to disagree. I think eventually you're going to have to make a bet on that. I think we all just kind of have a view on that sort of thing, and none of us ever gets validation about whether we answered it the way that we wanted to or the way that we didn't want to. There's no angel that just comes down and says, well, they were innocent or they were guilty. And similarly, there's no angel that comes down and says, oh yeah, no, people can agree to disagree. It's not a problem. You're just going to have to make a bet and you're going to have to go with it. Changing your mind is allowed, but it's a pain in the butt. It's totally allowed, and I encourage you to change your mind whenever you can. But I hope that a class like this, where, you're not going to remember the fine details of mixed strategy Nash equilibrium, okay? You might think that you are. You might have promised to yourself that you're going to remember exactly everything about mixing, and you've already forgotten it. It's okay. That's not my goal. My goal isn't just to teach you about these things, although I also suspect that if you came back after having forgotten it, you'd learn it faster than you did before. I also want you to just be ready for what's coming, the difficulties of this confusing reality that we live in, and the fortitude that it takes to make a bet. Because you don't get to know if you're right. And that's okay. You just have to make a bet. And things like Bayes' rule, or expected utility, or states of the world, these tools, although you may never use them again, help you to develop the muscles that it takes to make bets boldly and in a principled way. You might never become a trial attorney, but you may become a juror, and you'll have to make a bet. You'll have somebody's life in your hands, and you'll have to make a bet, and you won't get to know. How do you do so in a way that you can sleep at night? When you don't get to know, when you don't get to know the consequences, when you don't get to know, how do you make principled choices in a way that lets you sleep at night? How do you know? You do it by digging in the dirt like this. You do it by playing in stupid mathematical sandboxes. That is what is going to allow you, if you let it, to sleep at night, knowing that you're never going to get to know if you made the right choice. Incomplete information is a great chance for us to reinforce the importance of humility. You don't get to know, but also to say, and that isn't so bad. Because there are principled ways to go through that process of navigating all this uncertainty that isn't just aleatory and isn't just strategic through mixing, but actually taps into your own limitations and your own unique wrinkles about how you evaluate evidence. So even if you forget everything after this class, which is a near certainty, I hope you remember that. I hope that you remember that there's more to learning something than just remembering it. And that's why I really mean it every time that I say, thanks for watching.